In the heart of Skull Island, a terrifying spectacle unfolds. King Kong, our colossal protagonist, finds himself at the mercy of monstrous insects. Giant beetles, their mandibles snapping with prehistoric fury, swarm and attack. Enormous stick insects, their spindly legs longer than a man is tall, tower menacingly. This iconic scene from King Kong, while fantastical, prompts a question: could such gargantuan insects ever exist in reality? The answer, like much in the natural world, is complex and fascinating. Insects, those ubiquitous creatures that inhabit virtually every corner of our planet, are subject to biological laws that dictate their size. Their exoskeletons, while providing protection, also impose limitations. The very air they breathe, specifically its oxygen content, plays a crucial role in determining their maximum size. To understand why the giant insects of Skull Island remain firmly in the realm of fiction, we must delve into the fascinating world of insect biology and the environmental factors that govern their evolution. Insects, unlike humans and other vertebrates, possess an external skeleton, or exoskeleton. This tough, protective outer shell, made primarily of chitin, provides structural support and shields the insect from predators and environmental hazards. Think of it as a suit of armor, encasing the insect's soft tissues and vital organs. However, this protective casing comes at a cost. Exoskeletons are heavy and inflexible. As an insect grows larger, its exoskeleton must also increase in size and thickness to support the additional weight. This leads to a phenomenon known as the square cube law. As the dimensions of an object increase, its volume grows faster than its surface area. For insects, this means that a larger exoskeleton becomes disproportionately heavy and cumbersome, hindering movement and agility. Imagine a beetle the size of a small car, its exoskeleton thickened to withstand its own weight. Such a creature would be incredibly slow and vulnerable, unable to escape predators or effectively forage for food. The exoskeleton, while essential for survival at smaller sizes, becomes a liability as insects approach gargantuan proportions. This biological constraint effectively limits the maximum size that insects can attain, preventing them from reaching the monstrous dimensions depicted in King Kong. Another crucial factor influencing insect size is the concentration of oxygen in the atmosphere. Insects, unlike many larger animals, do not possess lungs. Instead, they breathe through a network of tiny tubes called trachea, which deliver oxygen directly to their tissues. This system, while efficient for small creatures, becomes less effective as body size increases. During the Carboniferous period, atmospheric oxygen levels were significantly higher than they are today, reaching up to 35%. This abundance of oxygen allowed insects to grow to extraordinary sizes, as their simple respiratory systems could still supply their tissues with sufficient oxygen. Giant dragonflies with wingspans of over 2 feet took to the skies, their metabolisms fueled by the oxygen-rich air. Today, atmospheric oxygen levels hover around 21%. This decrease in oxygen availability has had a profound impact on insect size. Modern insects simply cannot attain the gargantuan proportions of their prehistoric ancestors, as their respiratory systems would be unable to keep up with the oxygen demands of such massive bodies. The giant insects of King Kong, while visually stunning, remain firmly in the realm of fantasy due to the limitations imposed by our modern atmosphere. Section 4. Prehistoric Giants. When insects ruled the skies. The Carboniferous period, a time of lush swamps and towering ferns, witnessed the reign of giant insects. Dragonflies with wingspans approaching 2.5 feet soared through the air, their enormous compound eyes scanning the landscape for prey. Millipedes, some exceeding 6 feet in length, crawled along the forest floor, their segmented bodies resembling armored vehicles. These prehistoric giants provide a glimpse into a time when insects truly ruled the skies and the undergrowth. The reasons behind this gigantism are multifaceted, but the high atmospheric oxygen levels of the Carboniferous played a crucial role. With abundant oxygen available, insects could grow to extraordinary sizes, their simple respiratory systems capable of meeting their metabolic demands. The lack of large aerial predators during this period also contributed to their success, allowing giant insects to thrive without the threat of aerial attack. These prehistoric giants capture our imagination and remind us of the incredible diversity of life that has existed on Earth. They also highlight the profound influence of environmental factors, particularly atmospheric composition, on the evolution of life. The giant insects of the Carboniferous, while long extinct, offer valuable insights into the interplay between biology, environment, and the limits of size. Section 5. A World of Difference. Atmospheric Composition, Then and Now. The Earth's atmosphere has undergone significant changes throughout its history. From the early days of our planet, when volcanic activity was rampant and the atmosphere was thick with carbon dioxide and other gases, to the present day where human activities have become a major influence, the composition of the air we breathe has been in a constant state of flux. During the Carboniferous period, which spanned from about 359 to 299 million years ago, oxygen levels reached unprecedented heights, creating an environment conducive to insect gigantism. Imagine dragonflies with wingspans of over 2 feet and millipedes that stretched to lengths of 8 feet. These creatures thrived in an atmosphere where oxygen made up roughly 35% of the air, compared to the 21% we have today. This abundance of oxygen resulted from the rapid growth of vast, dense forests, which released vast quantities of oxygen into the atmosphere through the process of photosynthesis. These forests, filled with towering trees and lush vegetation, acted as massive oxygen factories, pumping out the gas as they converted sunlight into energy. At the same time, the decomposition of organic matter, which consumes oxygen, was relatively slow. This slow decomposition was due to the unique conditions of the Carboniferous period, where the climate was warm and humid, and the microbial life that breaks down dead plant material was not as efficient as it is today. This led to a net increase in atmospheric oxygen levels, creating a world where giant insects could thrive. Today the situation is reversed. The lush forests of the Carboniferous have long since turned into coal deposits, and the oxygen levels have dropped significantly. Atmospheric oxygen levels are significantly lower, hovering around 21%. This is the result of a complex interplay of natural processes and human activities that have altered the balance of gases in our atmosphere. This decrease is attributed to several factors, including the burning of fossil fuels, deforestation, and changes in ocean currents. The Industrial Revolution marked the beginning of a new era where humans began to burn large amounts of coal, oil, and natural gas, releasing carbon dioxide and other pollutants into the atmosphere. The burning of fossil fuels releases carbon dioxide into the atmosphere, which displaces oxygen. This not only contributes to global warming but also affects the delicate balance of gases that sustain life on Earth. Deforestation reduces the number of trees available to absorb carbon dioxide and release oxygen through photosynthesis. As forests are cleared for agriculture, urban development, and other purposes, the planet loses one of its most important tools for maintaining atmospheric balance. This dramatic shift in atmospheric composition has had a profound impact on the evolution of life, particularly on the size of insects. The lower oxygen levels of today mean that insects cannot grow as large as they did during the Carboniferous period. Modern insects, constrained by lower oxygen levels, cannot attain the gargantuan proportions of their prehistoric ancestors. The size of an insect is directly related to the amount of oxygen it can absorb through its respiratory system, and with less oxygen available, their growth is limited. The giant insects of King Kong, while captivating on screen, are a testament to the power of environmental factors in shaping the evolution of life on Earth. The changes in atmospheric composition over millions of years have influenced not only the size of insects but also the development of other forms of life, including plants and animals. Looking to the future, the composition of our atmosphere will continue to change. The choices we make today, from reducing fossil fuel consumption to protecting and restoring forests, will determine the air we breathe tomorrow. Understanding the history of our atmosphere can help us make informed decisions to ensure a healthy and sustainable environment for future generations. Scientists around the world are studying these changes using advanced technology to monitor and predict how our atmosphere will evolve. Their research is crucial in helping us understand the potential impacts of our actions and in developing strategies to mitigate negative effects. Global efforts to reduce carbon emissions and combat climate change are more important than ever. International agreements, such as the Paris Agreement, aim to unite countries in the fight to preserve our planet's atmosphere and ensure a livable future for all. But it's not just up to governments and scientists. Individuals can also make a difference by adopting more sustainable lifestyles, supporting renewable energy, and advocating for policies that protect our environment. Every action counts in the collective effort to maintain the delicate balance of our atmosphere. While the challenges are significant, there is hope. With continued research, global cooperation, and individual action, we can work towards a future where the Earth's atmosphere remains a life-sustaining force for generations to come. The story of our atmosphere is a reminder of the interconnectedness of all life on Earth, and the importance of preserving the natural systems that support us.